Okay, so I think it is a good idea to try to review the entire semester as quickly as we can. And it goes back to the fact that even though we call this a differential equations with linear algebra class, you could really call it a discrete and continuous dynamical systems class as sort of another name for differential equations with linear algebra. The continuous dynamical systems, CNTS is my abbreviation for continuous, corresponds to the differential equations, and the discrete dynamical systems refers to the difference equations. The difference equations, it's actually not the only name people use. Sometimes they call them recursive equations. It's another common name for them. Sometimes they call it iteration of maps, which really means functions. Map is another name for function. We are doing it most deeply in the case where you've got linear systems. And therefore, that's also another connection to linear algebra. But as we've seen recently, we're also doing nonlinear systems, at least of differential equations. We didn't really do nonlinear systems of difference equations so much. And at the beginning of the course, the idea is to connect them in terms of the simplest kinds of difference in differential equations and how to solve them. And going back to those simple ideas, it is something you should review and should be able to do. So for the difference equations, the simplest kind is, well, a scalar linear difference equation would be y sub n equals some constant a times y sub n minus 1. To find the next value of y, take a times the previous value of y. I think maybe I called it k instead of a back then. And assuming you've got a fixed initial condition y sub 0, the unique solution is found by iterating instead of integrating. It's kind of fortunate. Difference and differential both start with D, and iterating and integrating both start with I. How about that? Iterate the equation, keep going over and over again. That's how you solve a difference equation like this. Right? If yn equals a times yn minus 1, then yn minus 1 equals a times yn minus 2, which is a squared times yn minus 2. Iterate again. Yn minus 2 is a times yn minus 3. So you get a cubed times yn minus 3, etc. until you get down to, in the end, a to the n times y sub 0. The unique solution of this linear difference equation. Again, we call it a difference equation. Well, you might say in part because we could write it as a difference if we wanted to. Like that. Maybe that's a bad reason to call it a difference equation. I don't know. It's what people call it. So there we go. Solving it by iteration. Iterate means doing something over and over again. That's what we're doing here. With the differential equations, the corresponding differential equation is dy dt equals a times y. This is discrete. Here, y is a function of n, where n is 0, 1, 2, 3, 4, etc., a whole number greater than or equal to 0. This is continuous. Y is a function of t, a real variable. If we add a generic initial condition, we can write down the unique solution. To solve it, we've seen this enough that we know the answer by guessing. But if you didn't know how to solve it, you'd have to separate variables, which is something you should review as well, separating variables. The unique solution is y equals, well, I won't write a phi this time, y sub 0 times e to the at. What's the behavior of these solutions? It depends on a. in this case, you could say yn, at least in absolute value, goes to infinity if the absolute value of A is bigger than 1, right? If A were 2, for example, 2 to the n goes to infinity, 3 to the n goes to infinity, even 1.001 goes to infinity as n goes to infinity. This is as n goes to infinity here. There is an equilibrium point for the difference equation if your initial condition is 0, right? Yn would always equal 0 in that case. It's like an equilibrium point, but it would be a source because all other initial conditions would lead to points that move away from the origin. We never drew phase lines for things like this, but you could actually. They'd be discrete phase lines where you just draw individual dots showing the point as n increases. You wouldn't really draw arrows so much. So the points would go away from the origin. As n increases, it would be some sort of source. I didn't really emphasize that before, but you could say 0 is a source. On the other hand, the absolute value of yn goes to 0 if the absolute value of A is less than 1, like a half or a third. I am including absolute value signs here because technically A could be negative. Like, though if it were negative, like -2, think about what happens, that would bounce back and forth on a number line as it gets further and further from 0 if A were -2. Here it's going to go to 0 as n goes to infinity. If the absolute value of A is less than 1, 0 is a sinc. What if the absolute value of A equals 1? Well, if A is 1 itself, then you got 1 to the n, which is always 1. Every point on the number line you could call as an equilibrium point. It just stays where it is. Does that make sense? If A were 1. Every point on the number line would just stay where it is. If A were -1, they bounce back and forth. You know, if y0 was 4, then you go to 4, -4, 4, -4, 4, -4, you'd bounce back and forth. I won't bother writing that case. On the other hand, with the differential equation, it's not whether the absolute value of A is bigger than 1 or less than 1 that determines whether the origin is a sinc on a phase line for this differential equation. It's whether A is positive or negative. Right? If A is positive, that's exponential growth. The absolute value of y goes to infinity as t goes to infinity if A is positive. And the absolute value of y goes to 0 as t goes to infinity if A is negative. That's exponential decay. So it's not the exact same kind of condition. Here the origin would be a source, excuse me. 0 is a source on a phase line that I'm not bothering to draw. And here 0 is a sinc. What if A were 1? Excuse me, 0. Then your differential equation would be dy dt equals 0. All solutions are constant solutions. All solutions are equilibrium points. Your phase line would be infinitely many equilibrium points just staying there. The reason I bring this stuff up, I did talk about it some in the first few lectures of the class. The reason I bring this stuff up mostly is to emphasize the connection with higher dimensional systems where A is a matrix. We want to see connections here, right? If we're trying to summarize the course. If I change A to a matrix, if I change Y to a vector and A to a matrix, you know, you make everything capitalized and put little vector symbols above the Y's. You can basically say the same kind of things. That's essentially the beautiful generalization, except this little a to the n becomes capital A to the n. It's a matrix power. And this e to the at becomes the matrix exponential, which I typically write as e to the ta. That becomes a to the n. This becomes e to the ta. Typically put the t in front just to emphasize that t is a scalar getting multiplied by the matrix. That's what I call the beautiful generalization, that works. that we mostly focused on the matrix exponential case, that gives you your unique solution of the corresponding initial value problem. When y is a vector, an n-dimensional vector, and A is an n by n matrix. And these kind of conditions still hold here and here. If the absolute value of your matrix is bigger than 1 or less than 1, or if your matrix is positive or negative, but if the eigenvalues have those kind of properties. The A's become lambdas. If all your eigenvalues have modulus less than 1, meaning they could be complex eigenvalues, the distance to the origin in the complex plane is less than 1 versus, oops, that's supposed to be greater than 1 versus less than 1. If they're all greater than 1, then the origin is a source for the difference equation. If they're all less than 1 in absolute value, then the origin is a sink. If some of them are bigger than 1 and some are less than 1, then you got some sort of saddle point. Sink in some directions and a source in other directions. On the other hand, in the differential equation case, here again, lambda could be complex numbers. Same kind of thing could happen over here. It's really the real part of the lambdas being positive or negative that determines whether the origin is a source or sink. If there's a mixture, some of the eigenvalues have positive real part, some have negative real part. If they're all real, some are positive, some are negative, then the origin is some sort of saddle point. In the boundary case, where here the eigenvalues might have a modulus equal to 1, or here the real part might equal 0, then you might have some sort of center. Certainly in 2 dimensions, you'd have some sort of center going on. Those are in the differential equation case, that's the non-hyperbolic case where the Hartman-Grobman theorem does not apply, at least with linearizing nonlinear systems, which is not really what I'm talking about here. But in the linear case, when you have an eigenvalue that has a real part of 0, either it's the number 0 or it's a purely imaginary eigenvalue. In the 2-dimensional case, you get a center. If it's a purely imaginary eigenvalue, if it's a 0 eigenvalue, you get infinitely many equilibrium points. You get a line of equilibrium points, typically. In higher dimensions, even weirder things can happen, but we don't really get into that. And yeah, another theme is that we did apply this in the differential equation case, at least, to nonlinear systems through linearization, Jacobian matrix, and technically speaking, the Hartman-Grobman theorem is what you officially need to apply those ideas, though we took a more easygoing approach to that as far as doing homework goes. Okay, so that's a quick summary of the main connections between discrete dynamical systems, difference equations, and continuous dynamical systems, differential equations. In the systems case, both for difference equations and differential equations, in the systems case, n-dimensional vectors and n by n matrices, we also had the theory about diagonalization. Change of coordinates was a big theme as well. Why? Because diagonalization, change of coordinates, is a tool, a nice tool, when you think about it geometrically, especially for computing a to the n and computing e to the ta. Let's summarize the diagonalizability kind of stuff. In the nicest case, for I'll talk in generalities here. For A is an n by n matrix, A has n distinct real eigenvalues. In that nicest case, n distinct real eigenvalues. For most of our examples, n is 2, so that means 2 distinct real eigenvalues. That means A has n linearly independent eigenvectors. Remember, each eigenvalue actually has infinitely many eigenvectors that typically form a one-dimensional subspace of Rn. The eigenspace is one-dimensional typically. All non-zero multiples of an eigenvector is another eigenvector, but for the purposes of diagonalization, you only need one of them, right? For each eigenvalue, you find one of those. You put them in the columns of a matrix called P. And then if you compute P inverse AP, it becomes a diagonal matrix. That's going to be diagonal when the columns of P are the eigenvectors. And it's important that the eigenvectors be linearly independent so that they form a basis for Rn, so that the matrix P is invertible, so you can actually do this. Maybe a little bit of a mystery about why it works. I think I did talk about that in one lecture. I talked about details about why it works. Maybe you skipped over that. So it feels like a mystery. Why does this work? It's like magic, but it does work. And this does mean it's equivalent to saying A is PD P inverse. And it does mean two useful things. A to the n is ultimately, through a little bit of work, P times D to the n times P inverse, making A to the n easy to figure out because D to the n is easy to figure out. When D is diagonal, D to the n is very easy to figure out, right? You just raise the numbers in the main diagonal to the nth power and leave the zeros as they are. It's based on how we multiply matrices that happens. Of course, this still takes some work because P inverse in general is hard to find out. I mean, for a 2x2 matrix, it's not too bad. For a 3x3 matrix, it's okay. I'll do it if I have to. Once you get to 4x4 and a higher, P inverse gets to be a real big pain to figure out, even for computers once n is 10 or above. Computer programs can really bog down in computing inverse matrices, but it's still technically true and still could be useful. And we can also say e to the TA is ultimately, after some work, P times e to the TD times P inverse. So all that stuff is so that you can compute these things more easily. Of course, our main differential equations textbook doesn't talk about this stuff. Again, their goal is to get you to the general solution and solving initial value problems as quick as possible. So they just talk about writing your solution as a linear combination of the eigenvectors and solving for the coefficients based on initial conditions. And that's fine. But we want to connect it to linear algebra being the kind of course that we have. This is what's really going on in the background is the idea. We could also mention this is related to change of coordinates. Change of coordinates matrix that goes back to talking about vector spaces. P is a change of coordinates matrix. And without talking about the official idea of coordinate vectors, in the case of differential equations, I typically think of it as y equals pu. And I remember it that way because of pu, that it's y equals pu, not u equals py, which is equivalent to saying u equals p inverse times y. You can get from here to there by multiplying both sides of this equation on the left by p inverse. And using this idea, this is the change of coordinates. This is the new variable u. You should be able to verify, I think it came up on one exam, although it was in an abstract form, that du dt after some work is equal to du. And that is a completely decoupled system when d is diagonal. Now, our textbook talks about completely decoupled linear systems in chapter 2, actually. before, the main linear algebra chapter of chapter 3, because they are trying to illustrate that such systems are easy to solve. You can solve them just by looking at them, by guessing. You can figure out e to the TD very easily, effectively. We also talked about the flow ideas here, and so you should feel comfortable with that notation and whatever kinds of problems that shows up on. In the case of differential equations, we can write the unique solution of a generic initial value problem like this. And what is that? That's this. And I could label this with the flow notation. I could also call this fancy phi superscript t of y0. And when I think of it that way, I think of t as being fixed and y0 is the variable. It becomes here, when I think about it with differential equations, I think of y0 is fixed and t is the variable. It's technically a parametric curve as a function of t. It's actually a nonlinear function of t because t is in the exponent of the e. But if you think of t as fixed and y0 as the variable, e to the ta is a fixed matrix. That's just a linear transformation. And you can relate the differential equations and the difference equations. If you consider this difference equation, the point is that ultimately yn equals phi superscript n at y0. The flow idea generalizes to nonlinear systems, and I do talk about it in some of the lectures, but I haven't really, I don't really assign a ton about that, other than just working to try to understand the basic idea. So that's a quick summary of the main themes. Of course, there's plenty of other stuff that I haven't talked about here. Do you have any questions about the main themes? Can I clarify anything? These are the main themes as far as connecting differential equations in linear algebra. Of course, we did other stuff too. Maybe it's more useful to list that kind of stuff out, reminding you of things to review. So some other things to review would include going back to chapter 1 in the textbook, of course, separation of variables. For solving scalar differential equations, not necessarily linear, and also not necessarily autonomous, right? For example, dy dt equals, say, ty squared is an example of a non-autonomous scalar differential equation because the right-hand side depends on t as well as y. And it's also nonlinear because of the y squared. It's linear in t, but that doesn't matter. It's nonlinear in y, and that's enough to call it a nonlinear equation. If it were nonlinear in t, but linear in y, that is actually a linear equation. The key is whether it's linear in y or not. This is a nonlinear equation because it's nonlinear in y. In either case, should be able to solve it by separating variables because the right-hand side is a product of a function of t with a function of y. And after you separate variables, the integrals are not too hard to do, so you should be able to do that. Of course, I can make examples where it could be really hard to do, but I won't do that to you. Another technique is, well, undetermined coefficients. I'll just say UC. We did an example of that in class on Wednesday. Integrating factors, we did with the same example in class on Wednesday. Those are the main symbolic techniques. There are, by the way, other symbolic techniques that we haven't covered in this course. I know Dr. Auk likes to cover them in just a plain differential equations class, but we've got other things to do. these are, I do agree with the authors, the most important ones to know. The other techniques that solve other kinds of differential equations are kind of a little bit more specialized. These are more general, and so I think that's why they're more worth teaching. We had other stuff in chapter 1 as well. We had, well, Euler's method as our numerical approximation scheme for scalar differential equations in chapter 1 and systems of differential equations in chapter 2. And then more importantly to me for this classes in chapter 1, it's phase lines. Well, okay, let's start with slope fields and phase lines and bifurcations. Slope fields can be drawn for any kind of scalar differential equation of this form. It is a first order equation involving only a first derivative, no second derivatives. But it could be non-autonomous. You could have both y's and t's on the right-hand side. It also could be nonlinear. You get a computer to draw the slope field, meaning the little slope marks in the ty plane, and your solutions have to follow those because you're saying you want the slope of your solution curve at any point to equal the output of this function. F, of course, is not a solution function. It's the right-hand side function of the differential equation. What does it mean to solve such a differential equation? If y equals phi of t is a solution, that means phi prime of t equals f of t of phi of t, no matter what t is. You replace the y in both cases with phi of t, and dy dt is, because of that, is phi prime of t. The t is just a t. Of course, sometimes we have problems where you just should be able to check, is this function a solution or not? Left-hand side, right-hand side, plug it in, simplify, see if you get the same thing. And again, you can draw slope fields for them, even when you can't solve them. These qualitative methods, another main theme of the class, qualitative methods like slope fields, like phase lines, like phase planes, can be done even when you can't find formulas for solutions. So that's a nice, useful thing. You can figure out what's going to happen in some circumstances with technology help, even when you can't find formulas. That's a good thing. If you want more precision in numerical approximations, then you need a numerical method. Euler's method, to tell you the truth, is not the best method. If you have a hankering to take a numerical analysis class, one is being offered in the spring. And at the end of the semester, we do and go into more depth than Euler's method. We talk about ultimately something called the Runge-Kutta method is the best method, though there are variations on that. You might also get that in one of your physics and engineering classes as well. Phase lines are only for autonomous differential equations, so the right-hand side only depends on y. That's the only place where we draw phase lines. Bifurcations, and I could also add in here linearization as well. We had the linearization theorem, the one-dimensional version in chapter 1, which is a precursor to the Hartman-Grobman theorem. Bifurcations are when you get changes in the, for example, number of equilibrium points as some parameter changes. Of course, main kinds of exam problems I give are where the right-hand side function is quadratic, so you can use the quadratic formula as a shortcut for finding bifurcation values. I don't typically give harder problems on exams, though I could. Maybe if that were a cubic function or something, I could make it harder. But I don't, especially on in-class portions. Anything else in chapter 1? Interject if you got a question, if you want clarification on anything or something. You're wondering if something might show up on the test. You got lots of questions? Is that it, Caleb? Okay, I don't know what I said. It was so funny. Oh, it's the face. I see. How long has that been there? So I need to not allow that kind of thing to happen here. Huh? I need to know that for the future. How do I do that? Disable annotations for others. There we go. How long has it been there? Wow, okay. You just couldn't hold it in anymore. That should have been a joke for years to come that I never saw it. Right. All right. What did we talk about with linear algebra back then? First month or so of class. It was mostly about vectors and matrices, systems of equations, kernels and images of linear transformations correspond to null spaces and column spaces of matrices. I guess this does beg a question. Could any take-home question? This begs a question. Could any take-home question come up on the exam? Not in its full difficulty, probably, but maybe easier versions, right? Because the take-home questions could take a while. I don't want them to take a while, both for your sake and my sake. Let me say take-home questions could, besides in-class versions, take-home questions could show up on the final in simplified forms. What am I thinking of? I'm thinking of there was like a question on a take-home that was like a 4x3 matrix, and I said, I think find a basis for the kernel and the column space. If such a thing showed up in the final exam, it would be more likely to be a smaller matrix, 2x2 or 2x3, maybe 3x2. Of course, calculators seem to have trouble with tall and skinny matrices. So I guess if I'm going to put it on the final exam, it's got to be a short and wide matrix, like a 2x3 instead of a 3x2. So you can use the RREF on your calculator. Write a kernel, or in other words, a null space of a matrix in parametric vector form based on finding, going to RREF, identifying free variables, solving, writing it in vector form. Should be able to also relate that to finding a basis for the kernel. Basis for the column space is really easy. It's just a linear, describing the column space in parametric vector form is really easy. It's just a linear combination of the columns. However, finding a basis for it, you do have to go to REF because you got to identify the pivot columns. Real quick reminder of some things there. Okay, if I just remind you verbally without writing it down. With vectors, I mean, there's the basic stuff about vector addition and scalar multiplication, of course. There's computing dot products and finding angles between vectors. Might come up on exam 1. Finding projections of one vector along another. We did back first few weeks of class, but we also have done it recently. What else? Finding inverse matrices, multiplying matrices, definition of matrix multiplication as a linear combination. That really is a key thing. When you say A times X, what does A times X mean? Of course, you can do it by doing dot products of the rows of A with X. But it's important to realize what it means, because that connects it with linear transformation, for one thing. You can write down a formula like this, but you should also be able to describe it verbally. A times X, by definition, is a linear combination of the columns of A, where the components of the vector X are the weights, the coefficients in front of the A's, scalars. That's called a linear combination. And then A times B, where A is M by N and B is N by P, say, if you write out the columns of B, there's P of them. By definition, this is a matrix with P columns, where the first column is AB1, the second column is AB2, etc. The Pth column is ABP. And you should be able to look at this and think about dimensions. There's P columns in B, but since B has n rows, these are all vectors in Rn. And therefore, A can be multiplied by them, because as vectors in Rn, we would represent them as n by 1 column vectors. A's got n columns, so you can do the multiplication and get these vectors. And each of these is a vector, an m-dimensional vector. These are all in Rm. M by n matrix times n by 1 vector gives m by 1 vectors. And the final answer here is an m by p matrix. M rows, these vectors all have m entries, and p columns. The reason you multiply matrices this way is so that it corresponds to function composition when you think about the corresponding linear transformations. That's the reason why this is a good idea. I won't show you the details. Other stuff, going back to differential equations, included existence and uniqueness. Both in chapter 1 for scalar equations and chapter 2 for vector equations, nonlinear systems. And the most important consequence of this was with uniqueness, when you had a nonlinear but autonomous vector field for your right-hand side, which, in chapter 5 became systems of nonlinear equations that corresponded to, for example, competing species models and so forth. Is that distinct solution curves in the phase plane, if it's two-dimensional, can't touch each other. They could get arbitrarily close together as t goes to infinity, but they can't touch. Though you can have periodic solutions, a solution can come back to where it starts. And the main example, interesting example that I talk about in the lectures where that happens is called the Van der Pol system. And I also bring that in when I talk about trapping regions, which you should know the basic idea about as well. Other differential equation stuff in chapter 4 was the forced harmonic oscillators. And we had things like the beating phenomenon there, when the right-hand side forcing function was cosine of omega t, say, and using complexification came into play. When we did undetermined coefficients for the complexified equation, the undetermined coefficient ended up being a complex number. This came up on the last exam, whose distance to the origin in the complex plane is the amplitude of the sinusoidal forced response, which is also called the steady state solution. And its angle is related to the phase. Most of you did pretty well on that problem, I think, in the last exam. And yeah, then there's all the nonlinear stuff in chapter 5 and the Laplace transforms in chapter 6, nonlinear stuff. And Laplace, and you're still working on Laplace transforms, still working on trying to understand that. And that's something you should continue to work on before the final in a week. Any linear algebra stuff I'm forgetting? Yeah, I guess I'm forgetting about the vector space theory, linear transformations being operation preserving. Coordinate vectors, those kinds of ideas are something you should review as well. But I think that pretty much hits the main highlights.